Hello. Good morning. Hope you guys had a great fall weekend. Today's video is going to be about something that we call implicit differentiation. This is going to go along with section 3.8 in the textbook, in case you're wondering. But yeah, so let's jump in here. So suppose that I have a circle. Okay, so there's a circle. And let's say that the equation of this circle, this is a circle centered at the origin, is x squared plus y squared equals 4. Okay? And this point right here on the circle, we're going to say is, well, that's not right really. I want to put it. This point right here is x equals 1. Hopefully you can compute that y equals the square root of 3. Okay? So right there I'm sitting at that point, and I'm interested in, at that point, I'm interested in the slope of that line there, the slope of the tangent at that point. Okay? Now one of the things that you have to say to yourself, or hopefully maybe you're noticing is what do you notice about this equation for this circle? It's not y equals a function of x. This is an equation involving x and y. Okay? So our traditional method, right, that we've got, that we have right now to finding the slope of that line is, we find the derivative, and then we plug in x equals 1. But this equation involves x's and y's. So we have to come up with some sort of way of doing that. Now, one way would just be to solve this for y. I mean, y is the square root of 4 minus x squared, isn't it? I mean, we could just really quickly solve that. Actually, it's plus or minus, so the top half would be the plus, and the bottom half would be the minus. But then that's got a radical in it, and I don't know that we want to mess with radicals. So we're going to learn a new technique here called implicit differentiation. And so what implicit differentiation is really, it's an extension of the chain rule. We're going to start with our equation, x squared plus y squared equals 4. And then we're just going to differentiate this thing. Our goal is that we want to find dy dx. Okay? Because dy dx is going to be the slope of that tangent line. Dy dx is going to say, how is y changing for really, really tiny changes in x? What is y doing? That's what dy dx is. That's the slope of the tangent. Okay, so we're going to find dy dx. So we're going to differentiate this with respect to x. We're going to differentiate both sides of that with respect to x. Okay? So when I differentiate 2x squared with respect to x, I get 2x. And then when I differentiate y squared with respect to x, now we've done this already, and we just didn't call it implicit differentiation. We called it the chain rule. But when we do differentiate y squared with respect to x, we get 2y times dy dx. And that's sort of the implicit differentiation piece of that, is when we take the derivative of something that's a function of y that really is implicitly a function of x, like there's an implicit relationship, there's an implied relationship between x and y there, we just multiply, we do 2y, the derivative of the whole thing, times the derivative of the inside. And then the derivative of 4 is 0. Okay, and now we'll solve this for dy dx. So 2y times dy dx equals negative 2x. So dy dx is negative 2x over 2y. Or dy dx equals negative x over y. Okay? Now, what's the significance of that answer? Okay? That result now, okay, I can go over here to this point that we were after and say, okay, well, what was dy dx at the point 1 radical 3? And I can just say, oh, that's equal to -1, negative x, over radical 3. Okay? So that means the slope of this green line is -1 over radical 3. Okay? And we're just going to leave it like that. We'll leave it as -1 over radical 3 because rationalizing 1 over radical 3 is stupid. Now, let's talk about this answer a little bit more. It's negative, right? Should it have been negative? Yeah, that tangent line has a negative slope there, doesn't it? Now, we're not going to say that this function is increasing or decreasing there necessarily. I mean, because again, this is an equation involving x and y. It's not it's a relationship involving x and y. It's not necessarily a functional relationship. In fact, this isn't a function. Consequently, if you go down here and you put a dot right there, which would be at, I guess, 1 negative radical 3, correct? And we looked at the equation of the tangent line right there, or the slope of the tangent line right there, what's it going to be? It's going to be positive 1 over radical 3. So these two slopes are opposites, okay? So that's sort of the background of implicit differentiation, and a nice, cute example of how it works. You know, you're going to find dy dx, and your answer is going to be in terms of x and y. So what I'm going to do now, we'll erase this board, and then we'll do some examples of just calculating dy dx using implicit differentiation, so you can get kind of a feel for it. Some of those examples will involve the product rule and things like that. Okay, we're back. Got a clean board here, and we got an example here on Flannel Monday. So I'm going to tell you a quick story. When I learned implicit differentiation in high school, whenever that was, 20-some years ago, 30 years ago. I don't think it was 30, but it's almost 30. Gosh. Anyway, I can still remember, I could actually probably find some old tests that I saved because I was nerdy like that, where my teacher would write product rule, because the temptation when you're doing implicit differentiation is to forget the product rule. Okay, so here's our first example. We have x squared times y plus 2y plus cosine of x equals 10. And so our task is to find dy dx. Okay, let's find dy dx. All right, and right here we have to remember the product rule because you have a multiplication problem here, right? So we're going to differentiate both sides of this with respect to x. Okay, and then here we go. So the first, we're going to say it's the derivative of the first, 2x, times the second, y, plus the derivative of the second. What's the derivative of y with respect to x? Well, it's the derivative of y, which is 1 with respect to y, times dy dx. So I'll just put y dy dx. That's derivative of the second times the first. Okay? That's the product rule right here. Okay? Remember the product rule. Okay? I can still remember my test paper saying product rule in big red letters, -5. Okay? Plus, derivative of 2y is going to be 2 dy dx, plus the derivative of cosine of x is negative sine of x. And remember, when I'm saying the derivative of cosine of x, I'm really in my head saying the derivative with respect to x of cosine of x. And when I said the derivative of 2y, I'm really doing the derivative of 2y with respect to x. That's why it's 2 times dy dx. And then what's the derivative of 10? Is 0. And now you just got to put on your algebra pants here and solve this for dy dx. Okay? So anything that doesn't have a dy dx into it is going to go to the other side. I'm going to put the x squared first here. So that's going to equal sine of x plus 2x times y. And then I'm going to factor out a dy dx. Whoops. You see what I'm getting ready to do, and I was getting a little antsy. Now I'm going to divide. Okay, so there's our answer for dy dx. And yeah, it's a hot mess, okay? It is a mess. This is, just kind of a lot of algebra, but it's very doable. The key to this problem, the place where you're going to go bad, is right here, is that product rule. The derivative of the first, 2x, times the second, plus the derivative of the second, which is just this part right here, times the first, okay? So there's an example using the product rule. Let me erase the board. We'll do another one. This probably will be about enough that you'll need to see. And then we're good. So hold on. All right. So here we go. Here's another example. Task here still is the same. Find dy dx. Okay. So first thing we're going to do is we're going to differentiate both sides with respect to x. All right, so this is where Mrs. Austin would be like, product rule, and she'd write it, and then I would get -5 or -10. So here we go. We've got a chain rule and a product rule thing going on here, so this is going to be messy. So we're going to take the derivative with respect to x of secant of that quantity. So it's going to be secant of x squared y cubed, tangent of x squared y cubed. Now we got to multiply by the derivative of the inside, which is going to be the derivative of x squared y cubed. And the derivative of x squared y cubed is a product rule problem. So we're going to say, oh, that's the derivative of the first, 2x, times the second, plus the derivative of the second, 3y squared, times dy dx, times the first, x squared. Don't forget about the times the first. That's easy to do. Now the derivative of cosine y is going to be negative sine y times dy dx. The derivative of cosine of x squared is going to be negative sine of x squared times 2x. Oh man, I'm running out of room here. And the derivative of 3x squared on the right side is going to be 6x. Okay, so that's going to equal 6x. So now, essentially, the calculus is over, friends, because now this is just a giant algebra pants, maybe an algebra shirt, a little algebra suit, pop, perhaps. You've got to solve this baby for dy dx, okay? The calculus is over. So I'm going to distribute here. So this will be 2x y cubed secant of x squared y cubed tangent of x squared y cubed plus 3y squared x squared dy dx times all that mess, secant tangent. Right? And then minus sine y times dy dx minus sine x squared times 2x, and that's still equal to 6x. Barely fit all that on there. I should have started a little bit more to the left. Okay, now anything that doesn't have, so this is a term, this is a term, this is a term, this is a term, and then 6x is a term. Anything that doesn't have a dy dx with it is going to go whoosh to the other side. So 3y squared x squared dy dx secant of x squared y cubed tangent of x squared y cubed So that's going to go over minus dy dx sine y. And now everything is going to go to the other side. So that'll be 6x minus 2xy cubed secant x squared y cubed tangent x squared y cubed. So that's gone. That's taken care of. That's taken care of. Plus sine x squared times 2x. I think everybody's there. Now we're going to factor. So this is going to be 3y squared times secant x squared y cubed tangent x squared y cubed. Okay, this is a nasty problem. And if we can do this algebra, we could probably do any. Minus sine y equals 6x minus 2xy cubed secant x squared y cubed tangent x squared x squared y cubed plus sine of x squared times 2x. And now we get to divide. Whew. And fortunately, we barely have enough room left here for the very end, the big finish. So it's going to be 6x minus 2xy cubed secant x squared y cubed tangent x squared y cubed plus, I'll put the 2x in front, 2x sine of x squared over 3y squared secant of x squared y cubed tangent of x squared y cubed minus sine y. Whew! And that's dy dx. Woo, baby. What a mess. Okay? Yeah, so really, it's like always, I mean, I say this a lot of times, but in this problem, the calculus was over right here. The rest of this was algebra. So if you can get this step, and you're flumbling around to get to down here, okay, it's not calculus that you're having problems with, it's algebra that you're having problems with. And you're probably just trying to do things too fast. So, you know, take your time. I'm going to give you fewer problems that you can take your time on, rather than more problems that you want to rush through, okay? So, let's just kind of recap here, make sure we understand what happened. So, I took the derivative with respect to x of this whole equation, both sides of that equation, okay? And so right here I said the derivative of secant of x squared times y cubed was secant x squared y cubed tangent x squared y cubed. And then I have to multiply by the derivative of the inside. And the derivative of the inside is a product rule, okay? And inside that product rule is an implicit differentiation problem. So the derivative of the first, 2x, times the second, y cubed, plus the derivative of the second, 3y squared dy dx, times the first, x squared. And that all has to be in parentheses. If you don't put that right there in parentheses, guess what? It's over. You're done, because you're never going to get it right. This has to be in parentheses, okay? Then plus derivative of cosine of y, negative sine y, times dy dx, okay? And then plus derivative of cosine of x squared, negative sine x squared, times 2x. And then the derivative of 3x squared is 6x, okay? Some folks, instead of using a dy dx because they're lazy, they, like right here, you know, instead of putting times dy dx, they'll put times y prime. They'll use y prime everywhere they use dy dx. And then they'll solve for y prime. I don't think our book teaches that method. I actually probably started off my career, my journey in calculus using y prime, and then I've since converted back to dy dx. I think I feel like it shows a higher level of understanding than putting y prime. I feel like, I don't know, I think sometimes kids just get into this habit. It's like, oh, you mean anytime I take the derivative with y, I just put a y prime? Yeah, that's true, but do you really know what's going on? I feel like the dy dx notation kind of re-emphasizes the idea that, hey, dy dx actually means the derivative with respect to x of y. So that's that. I'm going to pause this video. I'm going to erase the board. I'm going to show you one other example but first I'm going to check the time because I might make this another video. So stay tuned. Okay, I think I got time. This video is only 20 minutes right now, so I think I got enough time to do this last thing with you. Okay, so we're going back to that first example of that equation of a circle, x squared plus y squared equals 4, and I found the slope of that tangent right there at the point 1 comma radical 3. Again, 1 comma radical 3 comes from just, those are the values of x and y that make the equation true, yeah? Okay, and then if you remember, our value of dy dx at that point was negative 1 over radical 3. Our expression for dy dx, I guess I could go ahead and write that down, I believe was negative 1 over, well, it was not that, it was negative x over y. Okay? So now, our task, the thing I want to show you, our task now, is I want to find this. Okay, and I'm introducing this notation to you right now, because I think, I'm not sure that we've experienced this notation. Okay? So what do you see when you see that? What are you thinking? A lot of people are like, oh, that's the second derivative. Well, yeah. Maybe let's expand on that a little bit. So what this means, it's actually the derivative with respect to x of dy dx. It's just this is how we write it. Okay, this is the shorthand way of writing this. The derivative with respect to x of dy dx. And we sort of have alluded to this in the past. What does this second derivative tell us? What is this derivative with respect to x of dy dx? It tells you how the slope of the tangent is going to change as you change x. That's what differentiating with respect to x means. As you change x, what happens to dy dx? Okay? And we kind of have learned already that sort of is connected to concavity. That when the second derivative is positive, your curve is concave up. And when your second derivative is negative, your curve is concave down. Meaning that when your second derivative is positive, your tangent lines, if you're concave up, tangent lines are getting steeper, getting bigger slopes as you move left to right. Okay? So we're going to find the second derivative of this guy right here. So I want you to differentiate with respect to x, negative x over y. And guess what? This is an implicit differentiation problem. So let's do it. Now, sadly, this is one case where I can't avoid it. Well, I can't avoid it if I really wanted to. But we'll use the quotient rule to do this. Okay? So we're going to take the derivative with respect to x of negative x over y. And that's going to equal that second derivative. Okay? So let's do it. So we're going to say that's low d high. What's the derivative of negative x with respect to x? It's negative 1. Minus high d low. What's the derivative of y with respect to x? Oh, it's dy dx. Over low squared. Okay? So now if I clean this up just a wee bit, I'm going to get negative y plus x times dy dx over y squared. Okay, that's second derivative. Now I don't have to factor or anything here because I've already got it solved for the second derivative. Now yes, that second derivative is in terms of dy dx. That's okay. All right, now let's just real quickly, for funsies here, let's find the value of that second derivative at the point 1 comma radical 3. So we're going to plug in these values. We're going to plug in negative radical 3, negative y, plus x, which is 1, times dy dx. Now, I could plug in negative x over y, or I could just plug in the value of dy dx at the point 1 radical 3, which I know is right there. So that's negative 1 over radical 3 over low squared. And there it is. Okay? So when I do the math on this, okay, this has a value right here. But you can probably pretty easily see that this value is actually less than 0 because you're going to have a negative quantity on the top over a positive, right? So this second derivative value that we're talking about is negative, and that should not surprise us because if we go back here and look at this point, take a look at this curve right here at that point. The curve right there is concave down. And when d, the second derivative, is positive, we would be concave up. So down here at this point where we talked about earlier, if we calculated that same second derivative, we would have gotten a positive number here. It would be a very similar positive number, actually. It would just be positive in the numerator. Okay? So that's how you calculate that second derivative. I'm introducing this to you right now, and we're going to come back to this over and over and over again, because when you see this, what I really, really want you thinking about is this right here is actually the derivative with respect to x of dy dx. Remember, when you see d over dx, that's like a command. Take the derivative of, with respect to x, of whatever is next to it. Okay? So I'm going to have some problems for you guys to work on today in this rainy Monday. And that's it. Take care.